Today we will discuss about this problem. So that a semiconductor has minimum conductivity at a given temperature when n equals to ni root over mu h by mu or p equals to ni root over p mu e by mu h. That means what is the condition at which a semiconductor conduct minimum conductivity? So let's start. Suppose the conductivity of the semiconductor sigma can be written as n into E into mu E plus P into E into mu H, where this is the equation number 1, where n is the electron concentration, that means electron concentration or negative charge concentration, and P is the hole concentration, and mu E the mobility of electrons, and mu H is the mobility of hole. So this is the equation of conductivity of a semiconductor. Now from mass action law we can say, that negative concentration and positive concentration is equals to Ni square, where Ni is the intrinsic concentration. So Ni is the intrinsic concentration. So this is equation number 2. So from this equation we can say that P is equals to Ni square divided by n. So suppose this is equation number 3. So from equation number 1 and 3, we get sigma is equals to n e mu e plus, this is the P, so this is Ni square by n e mu h. So this is the equation number, suppose 4. We have to prove that what is the condition for minimum conductivity. So this term sigma should be minimum. So what is the condition of a function that should be minimum? The condition is, so the condition for minimum, of the function sigma is first derivative with respect to the negative concentration of this semiconductor. So d sigma by dn must be equals to 0. This must be equals to 0. This is the condition that a function should be minimum. Okay, this is the condition. So if I take the first derivative of this term sigma with respect to n, so it will be, this is n, so it will be e mu e. So this is the, if I take first derivative of this term, then this term will be 1, so e mu e. If I take the first derivative, then it will be minus ni square divided by n square into e mu h equals to 0. This first derivative must be equals to 0. So from this equation we can say that E mu E equals to Ni square by N square E mu H equals to mu H. So this E cancel out. We should calculate what is the value of N. So from this equation we can say N square equals to Ni square into mu H divided by mu E. So then it will be N equals to Ni root over mu H divided by mu E. This is the condition for minimum conductivity. So this is the condition. So N must be equals to Ni root over mu H by mu E. This is the N equals to Ni root over mu H by mu E. Okay. Now if you want to calculate this condition in terms of positive concentration, so then it will be, so if you want to calculate this condition, then you have to calculate the number of N. So N must be equals to Ni square by P. This is equation number 3. So this equation will be from 1 and 3 we will get sigma equals to, this is Ni square by P E mu E plus P E mu H. This equals to, this equation will be 4. So for minimum condition, so for minimum of function sigma, this must be equals to d sigma by dp is equals to 0. So if I derivative this function, so then it will be minus Ni square by P square E mu H plus E mu H equals to 0. So from this equation we can say that this term will be here, so it will be mu E into mu H equals to Ni square by P square into E mu H. So this is not mu H, this is mu E. This is mu E and this is mu H. So it will be mu E. Okay. So this cancel out. So from this equation we can say that P square equals to Ni square into mu E by mu H. So P is equals to Ni root over mu E divided by mu H. So this is the two conditions. This condition is in terms of negative concentration and this condition is in terms of positive concentration. So this is the condition at which the semiconductor conduct minimum